Our project is tilted toward a future of alternative fuel transportation. Our team, which consists of myself, Lalit Davis, and my partner Ben Ringerman, looked at alternative energy scales, production, and performance, as well as the overarching business problem. We also investigated the traffic and road infrastructure as consideration of that business problem. The goal was to quantify the preconceptions about alternative energy as a method of transportation and evaluate it as a system problem in the context of traffic and infrastructure. Let's begin by exploring some preconceptions about transportation and vehicles in general. Take, for instance, the American diesel truck and the electric Nissan Leaf. The diesel truck, which can go off-road, has high performance, robust appearance, and epitomizes the many preconceived notions of American transportation. Then we have the Leaf, which is compact, slow, limited to paved surfaces, and most importantly, it has limited performance and range. Which would you rather drive? Now, how about these three images of traffic in LA, New York City, and Chicago? What are our preconceptions about traffic, infrastructure, and travel? According to the U.S. Government Energy Information Agency, on average, more than 393 million drivers each consume 332 gallons per year. With an average gas price of $3.56 per gallon, the cost of gas for a driver is more than $1,182 per year. The market for electric cars is slowly expanding. While the most common electric cars are hybrid models like Chevy Bolt or Toyota Prius, car manufacturers are beginning to market fully electric consumer options like the Tesla Roadster, Mitsubishi i-MiEV, and the Nissan Leaf. The negative preconception with electric cars include high MSRPs, limited distance capabilities, and extensive charging time. Unless more quick charge stations appear on commuter routes, these cars' owners are limited and average about 100 miles on a full charge. However, the future is still very bright for electric vehicles. Look at the Tesla Model S, which has an electric range of 265 miles, or Porsche 918 hybrid supercar, a car with a speed of over 200 miles per hour that has a fuel efficiency which is 30 miles per gallon more than some previous models. Lastly, we have Ferrari F70 hybrid with a rumored 900 horsepower. So electric cars aren't as nerdy as some would preconceive, and the possibilities for better performance and efficiency are growing. Now let's look at how we use data mining to explore other aspects of this topic further. To address the concern about electric cars we mentioned earlier, we use the power of analytics tools and present the tableau graphic on this slide. Every small blue dot represents an electric car charging station. The blue and yellow overlays are per capita income. The 6 large orange dots are Tesla Motors' existing supercharger network, which is currently capable of charging 150 miles of driving range in 30 minutes. That is more than sufficient for daily commuting and is a time that will likely improve with increasing demand. Finally, the green dots are our extrapolation of Tesla goals to have superchargers all across the country. To find possible solutions to our business problem, we use the standard CRISP-DM model. The first step is business understanding. We have already touched on this in the previous slide, that is trying to use the tools and knowledge learned in this class to look at the future of transportation. Step 2 is data understanding. We had to decide what kinds of data and what kinds of metric and KPIs we could use to measure aspects of this problem. We chose to look at mostly historic sources comprising a 50-year span of gas prices, licensed drivers, number of registered vehicles, and fuel consumption, as well as traffic, income, and political aspects of the top 10 purchasing states of electric vehicles. We also used current lithium-ion battery prices to measure the possible current and future cost and utility of electric and hybrid vehicles. Step 3 is data prep. This consists of lots of time on Google, followed by converting KML map data, a form of XML, to something useful in our tools, and compiling historic data into a spreadsheet. Step 4, our tools of choice were Tableau and IBM SPSS. We wanted to use visual analytics as much as traditional data mining because of how well it conveyed our findings. Step 5 and 6 will be discussed later by my partner.
For step 2 of data understanding, Data understand to us meant defining KPIs which would relate to the traffic infrastructure and electric cars. We chose aggregate historical fuel use and costs, voting pattern, cost of internal combustion engines versus hybrid or electric vehicles, the range performance and other metrics of those vehicles, and also the number of drivers in the US and the number of vehicles registered here and the types of fuel. For step 3 of data prep, as Layla mentioned, we had to go to Google for many of our sources. What we came up with was the Department of Transportation. We found lithium-ion battery costs from the Argonne National Lab. We found various automotive sources from McKinsey & Company, Edmunds, and Autoblog. And we used Google Maps and other sources to create the KML data, which we then pulled out in Excel from the XML tags to get the geotagging to create our electric map.